So in the previous video, I briefly explained how I've started using new initializer called key uniform, and I've made this video because previous explanation on previous video was imperfect, not really uh, explaining it clearly. And now I've understood the reason behind it better than before. Yeah, So, first of all, why I've switched to using this initializer. In the past, before I was using the initializer called Xavier Uniform, but now I'm switched to this initializer. And the reason is how the neural network, or precisely forward propagation, is implemented. Well, yeah, or it depends on how forward propagation is designed. I mean, which activation functions being used. So as you can see, I use ReLU activation functions for the activation functions, and so this is the reason I use ReLU activation function. I It's recommended to use this initializer. So, and why? So the ReLU function looks like this. All the inputs that are negative or zero would be zero, and if otherwise it would just output inputs. So if it was like 1, 10, 5, it would output 1, 5, 10. So and so So if we use this value on first hidden layer, um, so this would be the input, and this is initialized. I mean, so this weights is equivalent to this, and if this was sampled from, like, let's say, normal distribution function, where maybe half of values would be in between negative, I don't know, the 0.05 to 0. If these values go through this relative activation function, almost half of them would be zeroed out, and you get half of the outputs that would be positive. But even these values are positive, it may be really small, like 0.0001. I mean, it might be really tiny. And if you pass these values to next hidden layer and another later, another hidden layer after that, you multiply these small values, and these values eventually get even smaller. And if the values get these small, it would lead to vanishing gradient descent, because these values are so small, it makes gradients really small. So when you're training neural network, you are trying to minimize your loss function, and by literally descending the parabola of the function. And if the gradients are so tiny, so let's say the function might looks like this, and you want to descend to get to the value that would make loss function 0, and you just started training, and so you want to go here, and you started from here. If the gradients are so small, it it would take so many steps or epochs to get to here, because the gradients are so small. It doesn't move forward or make any progresses. But the opposite is also true. If the gradients are so big, it it might pass the it might pass where you want to land and just go to the other side of the function, and that might happen if the output from ReLU is positive, but it's really large. The values are so large. So, anyways, this ReLU function is a bit tricky, and so what we want to do is trying to uh, keep the variance of inputs and variance of outputs almost same. So this is how um, we this is how computations are done on feed for a neural network. You multiply x and weights, and you here I don't have biases, but and you add, so after the multiplication with inputs and weights, you add them. That's how matrix multiplications are done. So this is the number of inputs. So this is the computation for the feed for a neural network. And like I said, because if you use ReLU, half of the values would be zeroed out. You multiply this by 1/2, even though you want variance of output to be equal to variance of input. And so you wonder, so what variance for weights you should have to achieve this? So you so so you switch this variance y with variance as x, because these are same. So when you do that, the equation is gonna be like this. And you divide by variance x, because you have variance x on both sides of equation. So now you'd have this, and you multiply by 2. And you divide by 1 over n to get 2 over n is equivalent to variance of w. So you want variance of weight, variance for weights to be 2 over n. And if we see how heat normal is implemented, I indeed have 2 over fan in, that this just means number of inputs. So this is how key normal was created to compensate for future ReLU that zeroes out half of the inputs. So yeah, to simplify, we use this initializer to prevent vanishing and gradient descent, but in more detail, this is how it was implemented, this function. So yeah, anyways, this is it for today's video. I just wanted to explain it more clearly. So yeah, thanks.